So we are going to solve a problem elevator rides today. Uh, Before starting a problem, I would like to say that guys, if you like what I am doing, if you like the solutions that I am making, then please give a like on the video or please write that down in comments so that I know that okay, so you guys are seeing my content and you guys are liking it, so I can keep continue. I can keep making this type of videos. Okay, so let's start with today's question. Elevator rides. There are n people who want to get to the top of a building which has only one elevator. You know the weight of each person and the maximum allowed weight in the elevator. What is minimum number of elevator rides you would require? Okay, and look at the constraints here. The number of people are very small. Okay, it's less than 20. Okay, so let's see. Let me first write down the input. Okay, so what we are given? We are given some people, and there is a lift which can hold maximum W weight. Okay, and we want to move every people from ground floor to a top floor with this lift. So now we can put some people in the lift and send them upwards. So what is the minimum time we want? We want to use the lift for minimum times. Okay, so or we can say how many minimum lifts we would require. Okay, so how many times a lift would be used to get on the top floor? Or you can say that how many lifts would be required. We can use one lift for 3 times or 3 lifts at once. So basically, how many lifts would require to get all the peoples on the top floor? Okay, we are also given the weight of each people. Okay, so how we can do this? Now, first idea which you would get is okay, so, what if we put the someone with the maximum weight? Okay, let's say the current capacity is W. We would store everything in a map, okay, and we would get what is the maximum we can put here, which is not overflowing the weight. So weight here is 10, so the maximum we can put is 8. Okay, so now remaining is W, the maximum we can put here 1. So now the remaining is 1. The maximum you can't put anything now. So now again, okay, 1 lift is now again remaining is 10. The maximum you can put is 6, and the maximum you can put is 4. So you would require 2 lift. Okay. So this is the first solution that comes to our mind in these type of questions. That is what if we put the maximum we can put, and then whenever we can't put anything, we would increment the count. What this idea would fail. Let me show. Suppose let us let be there are 2 lifts of size 10. Now there are 6, 3, and 2, 2, and 3. Okay, so these are 5 people and we want them. So according to this algorithm, what we would do? You would first put the maximum size people, that is 6. Now the remaining capacity is 4. You would again search for maximum to put, that would be 3. Now the remaining is 1. We can't put anything. Okay. Now here what we would do? We would put 3. We would put 2. We would put 2. Okay, sorry. There are 4 twos. Okay. Now again we would put 2. But now you can see now we can't put one more 2. Okay, now we can't put one more 2, so we would require a third lift for this 2. but then that is the wrong solution because instead, if we would have put a 2 here and then remaining 2 here, then we would have done it in 2 lists. Okay, so greedy fail. Do you know why greedy fail? Because for a given, let's say a given value 4, okay, and they are given some values 1, 3, 2, 2, 5. So there is no method here that will tell us that okay, so this would give us treat this question as suppose there is a number line. We are given some segments of sizes size 3, size 2, size 2, and we want to put maximum segments in this one segment. Now there is no algo that would tell us that how we can do this in an or without without trying every possible solution. Because if we put one segment here, then the remaining would be n minus 1. Okay. Mhm. How can I kill? Just a second. I hope you understood till here that why our greedy would fail. Now, what I'm saying that for this type of questions where we have to fit maximum things inside a range, the main thing is we have to try every possible combination because in every combination there is some remaining space. Okay, so that remaining space would what I'm trying to say, how can I explain this? Okay, let's say you are given some weights. You want to give me the maximum weight I can achieve less than 8 by adding this. Okay, no, no, this example would not work. I'm trying to show you guys something, but how can I say? I don't know how to explain that. Mm. Basically, what I'm trying to say, there is no greedy way to fit something in a box. So let's say if we are given some box and there are some objects, and what we have to do, we have to put as many objects as we can in this box. Okay, so there is no greedy way that by which we can put them in box. We have to try every possible combination. So here also we have to, for a particular fifth, we have to find every possible combination. What would happen if we first sent 1 and 3, then we send 2 and 4, like that. So, and that is possible here because there is only 20 people. There are only maximum 20 people. So whenever the constraints are this small, the uh, first idea in your brain should be bit mask TP. Okay, bit mask TP. What this means is, let's suppose there are 20 people. Okay, let's suppose there are this many people, and the we want to choose minimum number of lips. So what we can do, we can treat every people as binary number. Okay, that if we take these people or not take these people, if we take this or not take this, if we take this or not take this, and so on. So what this would give us? This would give us as a binary number for every configuration. If you want to take first, fourth, and sixth, this is first, fourth, and sixth people, then the RF position would be this. So for showing that we have taken for 1, 4, and 6, we are using this bit mask. What this is called? Bit mask. We are masking every position in binary value. So it would give us a value, and we would get total 2 to the power 20 possible uh, numbers. So that this value is less than 10 to the power 6. Okay, so that's why we can iterate through every possible what we say position or every possible mask there is. Okay, so from this what we can see, we want a position that is 1, 1, 1. In DP what we learned, convert the bigger problem into smaller problems. Okay, so what we want a position, let's say, what was the example? Example was for 4 people only. So we want 1, 1, 1, 1. We want, this is our final state. We want answer for this state. Okay, we want answer for this state when everything has reached the top. Okay, we are iterating one as this person is reached, this person has reached top. Okay, so to find this, what we can say, okay, let's iterate to every possibility. What I'm saying, for to get this state, which would be previous states. Okay, let's suppose we would look for every possibility from 1 to the 2 to the power n, that is from 0, 0, 0 to 0, 0, 1, 0, 0, 1, 0, like till 1, 1, 1, 1. Okay, so for this state, what are the states we can reach? Okay, so the first would be, we would check for every position, okay, whether we can reach from this state or not. The one thing you will notice that if we can only reach from this state to this state if there is no 0 here and there is 1 here. What I'm saying, that if let's say this is the state, this is the state we want to reach. Now we can't reach here from this state because there is already one person reached on the top in this, and we don't want that person to be on the top. Okay, so we can only reach we can only reach the states for any particular state. We can only reach by the states which has only the bit sets which are set in this only. So we can unset this bit, but we can't set already a set 0. Okay, so here what are the ways we can reach? If this is our position, then what are the ways we can reach? We can either reach by this or by this or by this also. Okay, so these are the 3 possible. So that way we will iterate from every position to every position. If there is any bit set in the position which is not set in our final destination, then we would simply continue. And if we found any number, let's say if we are considering these states. Okay, so now what should be added to this state so that we get this state? That would be our 1, 1, 1, 0. Okay, you can find this by simply OR, taking the OR of 2 values. Suppose this is the value. So what we do, we would do XOR, not OR, XOR. So 1, 1, 0, 1, 1, 1. Okay, the second state would be this. Now, if we know the answer for both these states, then we can simply do this plus this. Okay, so this would be a minimum. So suppose if for any state, and we would also check that if this we can take this we can take everyone as 0. Okay, what I'm telling that. So what are the, let me write down it clearly so you guys can understand. Let's denote it with a number int. That would be binary. Okay, so for int x, okay, now first we would find out the total weight of this current x. Means what much weight is there. So for this we would find the weight of all the set bits. So find total weight for every set bit. Now if this total is less than our capacity of lift, then we would simply return 1 because we can go there in 1 state. Okay, now if it's not 1, so it must be from some previous states because we can't reach that in one go. So what we will do, we would iterate from every I, that is we would consider every bit, every possible combination of this n people. Now if there are some bits set in y but not in x, so this is a false state. We can't reach x from this state, so we would continue. Just a second. Okay, sorry for the distance. Okay, so where were we? Okay, so if it's set in y but not in x, then we have to continue. Otherwise, we would find the second state, that would be x or y, and the answer and what we would return. Sorry, let's say answer is uh, answer would be minimum of every possible state. Now for this, solve for y plus solve for x. Okay, and at last, we would return the answer. So what we are doing, let's suppose what we want 1 1 1. So what we are checking for every possible combination, let's say if x is 1 1 0. So what we are checking, we are checking how what is the minimum for the what are the minimum lifts required for this state and what are the minimum lifts required for this state, and we would add this both. Okay, and we are checking for every possible combination. So this would eventually give us the minimum of all. Now what is the issue here is, let's say this is state. So for any given state, we are iterating every possible states. So a state can go from 0 0 0 to 2 to the power n, and in our case it is nearly 10 to the power 5. So it will give us TLE because it's 10 to the power 5 into 10 to the power 5. So now what we have to do, we have to eliminate this loop, or we have to eliminate it, or what we can do, we can improve it. So now let's improve it. How we can improve it? Okay, so let's say we want the answer for this state. So what we are doing, we are finding every mask of this, like 1100 is mask of this. So we are doing this, but now we don't want to calculate everything. Okay. Now what if, can we go individually, like to all n? Like we would have put the person here. Like there are three person to be. We want this 3% to reach the top. Now let's take these persons individually. Now we are not treating, we are not calculating for every answer. Okay, every combination. We are just calculating for what would happen if we have put on this person one by one. So what would have put on if we uh, now let's say for every person, let's take this person individually, and now this is our two states. Okay, but there is one more thing. Now, if you want to add this person to this position, what if with this position there was some space left in the lift? Suppose the lift capacity was 20. These two persons was waiting 15 in total, and this person was waiting, weight was 3. Now we would have also put these 3 directly here. Then also the answer for this state and this state would be same, that is one lift. So what we are adding? We are adding one more state. So previously our state was just this configuration. We can say this as configuration. Now if we add one more state to it, that is remaining weight. Okay. So what this remaining weight will give us? This will show for every configuration what we are storing. We are storing two values. The one is what is the minimum answer, minimum lifts required for this state. And one more thing, we are just adding one more thing. What was the remaining weight on last lift? Means if we have fully filled two lift and we have the minimum lift required was 3. Okay, so what we want, what was the weight remaining, because the third lift can be partially filled also, no? So we want what was the last we want what was the remaining weight of the last lift. So earlier we were just storing minimum lifts, but for this what was the limitation? Now we have to search for every state. So it was given as 2 to the power raised to square. So this was not possible because it would give us TLE. So now what we did, we modified our answer a little bit. Now we can't go for every state. So what we did, we are going for every n, that is every person, and we are checking if we can put this person in this configuration or not. Okay, because when we have put in some persons in lift, it would be man by man only. Like what I'm trying to say. Let's say this is the position which you have to find. Okay, so for this, let's say one position was this and one was this. Okay, so we have put this man in this. Now if you again expand this, it would be this only. So at the end point, what we are doing, we are just adding man with man. Okay. Earlier, what we are doing, if this all are possible in one lift, we are simply returning from here only that it would be one only. But instead of calculating for this whole state, what we are looking, we are just looking what if we go person by person. So for the final state, let's say, for if we are trying for this person. Okay. So what would be our remaining state? It would be this. Now what we are saying, what we want minimum lifts for this state. Okay. Now we in earlier we were simply adding these two. And why we were able to add these two? Because even earlier, why the second state was not required? Because earlier when adding, we were adding every state. So suppose this three with this 3%, the remaining weight, this 3%'s weight was 18, capacity was 20, and the weight for the first person was 2. So 18 plus 2 was 20. So if we go by previous method, here it would show 2. But that was not of any matter for us because previously we were checking every combination. So this would not give us the minimum answer, but previously we would have also checked for this state also. That what if we put everyone in single lift? So at that time, this would give us one answer, and this would be minimum. But now our constraint can't allow us to loop every combination. So what we did, we are going number by number, person by person. So we can add first person in this or not? How we can say? So that's why uh, we stored one more value in our answer, that is the remaining weight for this combination. So what this remaining weight would give us, that it's possible to reach this state with 3 leaves, with the last lift having weight left is 2. So now if you want to add this person to this combination, if the weight is less than the weight of this person, then we can add it without any issue. So now the answer for that would be 3 leaves only, but the remaining weight would be the weight for this person. Okay, so that would be 3 comma 0. And what if the weight was more? Okay, so if the weight for this person was more, so we are looking this state, we are looking for every person. If this person's for if the weight remaining after putting this 3% was 2. If its weight was 2 or less than 2, we would have put on it in same. So the minimum for this and this would be same. Now, if the weight for this is more, we would require one more lift. So now 3 plus 1. And now what would be the remaining? That would be capacity. And in new lift, what we put? We just put this new ones with this. We just put on this person. So it would be W minus 2. Okay, so you got it. So what we are doing, if I explain you iteratively, then you would know. Okay, so let's look it iteratively. Okay, there are 4 persons. You want to put them in a lift. Okay, earlier for 0% for this state, when everyone is 0, the answer is 0 lift and whole lift is empty. Now let's see if we can put this 1% in this state. Okay, we can put it because the weight lift is empty. So now this is our current state. We have put on this person in this lift, and our lift required is 1 because for this person we would require a new lift, and weight remaining would be this. Okay, now from this state, where can we go? We can put these 3 persons individually. Okay, so let me show you what we are doing. Okay, if now till now what I was showing that how we can reach a state. Now what I'm trying to show you is another method. Not another method, you can say another way to look into things. If you didn't understand from this, then this would help. Okay, so this is our now we are looking for from final state to bottom state. Now we are creating our final state. Okay, so this is our initial state, zero lift and whole empty. Now, what are the possibilities we can go from here? There are four possibilities because we have to put one person at a time. This is our constraint. And as I mentioned you, why we are putting one person at a time, because if we put multiple persons, then for every state we would require 2 to the power n. So this would be real. Okay. Why I'm repeating the same thing again and again? I want you guys to understand. I just don't want you guys to just mug up the problem like, okay, so this was done. I'm trying to explain you why it was done. Because if we were putting more than one person at a time, then we would have to choose that persons. Okay, so if we are just putting one person at a time, then okay. But if we want to put two-person at a time, then we want to choose the two-person. That which two-person we have to put. So that would give us the complexity of 2 to the power n, and that is expensive. We can't allow that. So what we are doing, we put a constraint that we are putting one person at a time, and we are seeing that how it will change our answer. So if we put one person in the lift, okay, so the new state would be 1000. Now from this state to this state, now we will see that if we can put this person in the same lift or not. So the remaining weight is okay. So first the lift is 0 and the remaining weight is also 0. So the remaining weight is 0, so we can't put that in same lift. So what we'll do, we would get a new lift for this person. Okay, so for this state, we got a new lift. So lift plus 1. And now what is the remaining capacity? In this new lift, only one person is standing. So that would be this only. So this is the remaining capacity. For this also, we would require something. For this also, and for this also. Okay, so these are the four states. Now from this state where we can reach, we will see that. Okay, so we will reach at a state. If we from this we can only reach three states. That is 1100, 1010, and 1001. As I said, we are adding one person at a time. So for this, what would be the answer? Now can we add this person in the same lift? So if the remaining weight, which was this, if the weight of this person is greater than this person, then we can't add it in this lift. So then we would require one more lift. So that lift count would be plus 1, and the space remaining in that new lift would be W minus W2. And now if this was greater than W2, then the lift count would remain the same because we can accommodate this person in that same lift. Okay, so through this recursion, now it will again repeat itself for 2 times. This also, now this will repeat 1 time only. Okay, so total how many times this recursion has gone on? Okay, so it would be from 1. So How we did? We added one person at a time. Okay, so that was it. So we covered by adding one person at a time. We cover every possible way. Now, things would have been different if we have put on the second person first. So we would also calculate for that. Things would have been different if we have calculated for if we put on the first person here. So we calculated for that also. And things would have different if we have calculated for this also. Okay, so now look at the time complexity for this. Time complexity for this would be we are for every because for every number we are having number of zeros. So that is n. Now that is decreasing by each height. Means as we are going deeper, the number of states are decreasing. Okay, so the first for the first call 0000, it would be n possibility. Now for each of this n possibility, there would be n minus one possibility. For each of this n minus one possibility, that would be this. So the time complexity would be n factorial. Okay. Now I know we can't allow n factorial. So what we'll do, we will memorize this. Now, how we can memorize this? Suppose we are at a stage here, 1100. Okay. And this is already giving us a combination for two left and two remaining. Now, from this stage, we are also coming to that position. Okay, suppose we are at this position. Now, if we would have reached this one time from here and one time from here also. Okay, the first time we reached here, we stored the answer was the lift required was 2, and let's suppose the remaining weight was also 2. Now, if for next time when we came to this state, let's say our answer is the lift required is 2, but here the space remaining is 3. Okay, so if this is the case, then we have to, because this is a better from this. Okay, this is a better state from this. What I'm saying that if you do this, what we were doing recursively. You can say it as DFS. We were first branch looking for one branch till the end. Okay, but what if I said that we do BFS? Okay, so what is BFS? So BFS is breadth first search. So we would find the answer for these three, this level, then this level, then this level. So how that will help us? Suppose if for this we can get answer from multiple ways. That is this. Okay, for this it's 2, but if it was more than 1, then we would have gotten from multiple branches. Suppose this is 3. Okay, so suppose this is the tree. So if we go to each node, the time complexity was n factorial. Now we can't allow that. So what we found out was that the node which were repeating, like the three nodes which were present here also, that they were present here also, and they were present here also. Okay, what I'm saying is the nodes are common. So if we go in breadth first manner, we would have solved this problem first here. Then again, when we got here, then if this version was better than this version, then yeah, we again have to calculate this again. And if we calculate it again here, if this version is better than this version, then we have to calculate it again. So that way, the earlier calculations were simply wasted. Okay. So what we can do, if we go in PFS manner, okay. So at a moment we have calculated this 4. Okay. Now we would calculate this. Now when we will calculate this, then these two states would be would have come multiple times. So one time it would have come for 2 comma 2. One time it would have come for 2 comma 3. Okay, so it would have come multiple times. Now if we have solved first this one, then uh, we would have evaluated every possible answer, and that would be a waste because we already have a better one. You guys know that if lift number required in first case and in second case, if lift number required is small, then this is a better case. But if lift numbers required are equal, if both the cases have same number of lifts, then the one where the space remaining is more, because then we can fit a person with higher weight also. So then we would look for the weight, and weight one should be minimum. The minimum weight one would be, sorry, the maximum weight would be considered. ओके, सो मैं क्या कहना चाहता हूँ कि समझ लो कि अगर हम लोग सपोज इफ वी आर from a point we can go to multiple points. Now you can see that at this level all nodes are different. Okay, so this is this. Okay, all nodes are different. But now again if you would have expanded it, then you would see that there are some nodes common. Okay, so we don't want these nodes to be explored individually. So that's why we would go by PFS manner. PFS manner means we would first find out these three. Okay, now these all four states are different. So we would now calculate for this all states. Now in this there would be some states that are common. So we would only consider the best case. So by considering this best case only, we have eliminated this whole tree, which would have formed because of this. Okay. So this way, what would now our time complexity would have increased, because now for every state we can see that with every increasing number, with every increasing depth, one number is being added. First it was 0. Now in this every element there is just 1%. Now there is just 2% for this whole tree. Okay. So now every possible combinations for this 2% would be here only, and we would only consider the best one. So the whole tree that would have formed because of this version which is not best would be directly eliminated. Okay, so this way this would improve our time complexity. Now, what would be the new time complexity? First, every state iteration is for every state we are iterating it. Okay, so that would be the numbers are 0, 0 to 1, 1, 1, 1. So that would be 2 to the power n. Okay, and we are iterating. We are finding for every state just one time. Okay, so we are just looking for every step. At every stage, what we are performing maximum n operations. So the time complexity would be n time. So I hope you guys understood what I was trying to say, like why we are going by TFS, BFS manner and why not TFS. Okay, you would understand it better from tabular view. We would go start from lower value. From this where we can go. We can go from this stage. We can go to this stage. We can go to this stage. We can go to this stage. Okay. Now now we would move forward. Okay, so we are now at this stage. Now from this where we can reach more 3 stages. Now we will increment our answer. Then we would have come to this. From here also we can reach multiple states. From here also we can reach multiple states. From here also we can reach multiple states. So what we will do? We would go from 0, 0, 0 to 1, 1, 1, 1. And for every possible state, we would try to add one person and see what would be the change. Okay. And we would store the minimum change from all the possible outcomes. So what I was what I was showing you guys here was TFS versus BFS. That is basically what we say memoization. Okay, so the the way the reason from which I say BFS is this memoization. So whatever you guys see in memoization, whatever you see, that is memoization. That is actually the BFS version of the TFS part. Okay, you would understand it better in the code. Now let's move to the code. Okay, so RTP or the state would store minimum required to take this one and one to take first and second to top, and how much it is remaining in the last delete. So what would be our max last bit? That would be 1 to the power 10. Okay, this gives us 2 raised to n. Okay, so we want 2 raised to the power n minus 1. This would give us 2 to the power n, and if we subtract 1 from it, this would be our last state. This is the last state. Now we would require a TP that would be a combination of pair. It would be mean leaf and weight remain. Now we will go from 0 to our last state. Actually, the last state calculation not required. Now for this state, we would go for we would look for every person. Now if this person is already there, means if we are looking for if the person is already uh, been there in the lift, so we can't add that person. So we would continue. So how we can check? If I space j, so this would give us the ptat by and it with 1. So what we are doing, if we want to check that this bit is present previously present or not. If it was previously present, then we would continue this because this person is already added. This person has already been added. Okay, so how can we check? We would right shift. Okay, so this right shift operation would have put this in front. Now we would simply AND it with 1. Now by ANDing it with 1, this all will become 0. Now if it was 1, then it will give us the answer 1. So in this case, we would not move forward with this. We would not add this person because it is already added. Now if this answer for this is 0, then we can add this person. So suppose if we are checking for this is 0th, first, second, third. So if we are checking for first bit, then by if we left it with j, then it would not move any bit. Now for this, now j is 1. So now this will be removed and this would be a first. So that's why this would give a 1 if that is present or not. So if this is already present, then we will continue. Otherwise, we would add it. So for adding it, we can simply do OR. Okay, so now if the weight of this person, the weight of jth person is greater than, okay, let us let us first abstract the answer. Lift required to reach this state and the remaining weight at this stage. So lift required if the weight is greater than remaining. So we would have to add new diff for this state. What would be a new state? That would be this will be simply A, so A or B, not B. it would be A or one right shift, left shift, J. Okay, so this would give us, so how we are getting the new state. Suppose this is the previous state. Now we want to add this. So we will do right shift one time. This would be J. So now the number is 10. Now we would OR. So by ORing this, we would get this stage. Okay, so we would perform OR operation. So by OR operation, we would get this stage. Now the value for this would be if this is greater. Okay, so because this is greater, the lift required, we can't put that in same lift. So new lift would be required and the remaining weight would be W minus V of J. Because in this new lift, only this person is present. So everything else is excess. Now, if the weight was less, so in that case, then the lift would be same only, but the weight was now less. But remaining weight was less. Okay, here we would make a new operation for, let's say, if how we have to find the max. Why we are taking max? Okay, so we are taking max. Why we are taking max? As I said, when we are reaching that position, suppose when we are reaching this position, okay, we want the minimum answer. There were multiple ways to reach from here. We have seen in this. But what we want? We want minimum answer for this. Okay, so we would be taking minimum. So that's why now we have to make a new function. Let's say okay, so we are making this new function. What it would take intake as input as paragraph into comma int. Okay, so if the first is if a dot first is b dot first, then what we would have written if both are equal. In that case, we would do second value. Second value should be smaller. Sorry, the second value should be bigger because the more the weight remaining, it's better. What would be your answer? So this is what they call bit mask TP. Okay, so we got our answer. The time complexity would be, as I told earlier, 2 to the power n, because these are the number of possible states into n. For each state, we are iterating n times. For this type of problems, I guess you should practice as much as possible. You can search for questions on bit mask TP and practice it. The only way to get better is just practice, practice, practice. Okay, no one can make you better. You can't be better by simply just seeing tutorial of every problem. You have to practice it on your own. Okay, so this got accepted. I hope now everything is clear to you. If you have any doubts or anything, you can just put it in comment. And if you guys really like, if you guys love what I am doing here, and if you want me to continue, then please give me a like. Okay, see you in the next video.